Hello and welcome to this section on limits at infinity and horizontal asymptotes. So we're going to be evaluating limits as the input variable x goes to either infinity or negative infinity. Another way to say that is that we are saying that the magnitude of x is made to be as large as possible. Okay, so the absolute value of x, okay, is approaching infinity, which means either x itself is going to infinity or x is going to negative infinity then, in the sense of the limit. And we want to know, well, what's happening to f of x? All right, what value does f of x approach? If it approaches a finite number, then geometrically or graphically, we would interpret that finite number as a horizontal asymptote. The equation y is equal to that number is a horizontal asymptote. If f of x instead is unbounded, if f of x goes to infinity or to negative infinity, then the limit would have gone to either infinity or negative infinity, and the graph would not be approaching a horizontal asymptote. If f of x were to not approach any particular quantity or direction, if it were, for instance, to approach more than one value, then we would say that the limit does not exist. So we're looking at limits of the type, the limit as, let's say, the absolute value of x approaches infinity of f of x. And we're trying to find out what that limit is. Okay. We'll begin by taking a look at the graphical intuitive definition of that limit. And we'll take a look at some basic functions. Y equals 1 over x to the r, where r is a rational number greater than 0. Y is equal to the arctangent of x, which is a graph that has two horizontal asymptotes. Y equals e to the x, which has a horizontal asymptote to the left as x goes to negative infinity, okay, but does not have a horizontal asymptote to the right. Yeah, so the limit to the limit as x goes to negative infinity, that would approach 0 from above, but the limit as x goes to positive infinity would actually go to infinity. And the graphs of y equals sine of x and y equals cosine of x, those are the wave functions. They're the same wave as each other. They're just shifted or translated by pi over 2, depending on whether we are starting at equilibrium or at a maximum or a minimum, to determine whether we're on a sine curve starting at equilibrium or a cosine curve when we would be starting at the maximum or the crest of a wave, as long as the amplitude was positive. So overall they're the same wave function. But because they go up and down repeating forever, then as we go out to either infinity or negative infinity, we would not approach any particular value. So for these curves right here, the limit as the magnitude of x gets large would in fact not exist. Fractional functions, those would be ratios of power functions. Now, power functions would be functions like x to the power of n, for example, where n can be any real number. Okay, I'll make n any real number. Okay, so we should make, if n is positive, and it was a positive real number, in fact, because otherwise, if we had n was a negative number, we could write the reciprocal 1 over x to the n, where n becomes positive, and then we could be talking about this case over here. But let's say we take that n as a positive, a real number then. So that would include that we could have fractional exponents as well as irrational exponents, and not just polynomial types. So we could be dealing with ratios of functions like, maybe roots or radicals, like a square root function divided by a polynomial function, for example. And then take a look at a few other interesting examples as well, which might tie into some previous content that we've seen. So let's start with taking a look at some graphs for the intuitive definition of the limit. So I pulled these from the textbook here. They're nice graphs, better than I could sketch real quick. Okay, these three on the left here are all describing horizontal asymptotic behavior. They would all be describing a limit as x is now approaching infinity. Notice that these are all going off to the right. The line y equals L is the horizontal asymptote that the function is approaching. As it goes off to the right, it doesn't speak about what's happening as we go off to the left. The limit as x goes to infinity of f of x is equal to L. And for this to be a horizontal asymptote, it must be that L is in fact a finite number. It could be positive, it could be negative. The idea is that we are approaching some horizontal line with the equation y equals L as x gets very, very large. Now, what does that mean that x gets very, very large? It means if you choose a number, let's suppose that this is stretching out way, way high, so the numbers are getting really large as we look out here. If you choose a really large positive number, and let's call that number n, then this statement is saying that for all, okay, it's saying for all, let me write this up. I'm going to write this up here instead. Okay. For all values of x that are greater than that big number n that you thought of, okay, the difference between f of x and the limiting value L, that is in magnitude, the distance between the two, would be less than epsilon, where epsilon is chosen to be any positive number, just like we saw recently with the epsilon delta precise definition of the limit. Okay. So limit as x goes to infinity of f of x equals L. Right? For any epsilon you could choose, no matter how small, as long as it's a positive number epsilon, it's saying that for any large number n you want to choose, that we're saying for all x beyond that, okay, then the distance between those two is less than epsilon. So for example here, let's say, so here's L, right? Let's say like L minus epsilon is around here. Okay, so this is L minus epsilon. And then let's say that this is L plus epsilon up here, right? So what we're saying is that eventually we're going to choose a value of n, okay, or sorry, for any n that we were to select, for every x, for every value of x that is greater than that n, you're going to see that the resulting function is bounded between the floor and the ceiling, L minus epsilon and L plus epsilon. And if you were to choose a smaller epsilon, if you were to update epsilon, okay, to make a smaller interval, then by the precise definition of the limit, okay, that would be to say that then you could choose a larger value of n, and now all values of x that are greater than that n, okay, for any value of x that's greater than that n, the point on the curve associated with that x would again be bounded, okay, between the floor and the ceiling, L minus epsilon and then L plus epsilon, for example. Okay. So as long as we're approaching a finite number here in closeness, then geometrically we say we're approaching a horizontal asymptote. This first picture here, image, is showing it approaching from below. We could also be approaching from above, and we can cross a horizontal asymptote one or many times. Okay, so we can have, for instance, like a sine wave function that is maybe bounded above and below. Okay, like we saw previously when dealing with the squeeze theorem. So it's possible to keep crossing the horizontal asymptote, but to continue to get closer and closer and closer to that asymptote, right? So that no matter what epsilon we choose, okay, we know that eventually the function is going to remain within those bounds. So it's going to be close enough to that horizontal asymptote. Okay, that's the precise definition of the limit at infinity. The book has a nice applet in it that puts this in an animation. I'll take a look at that in a moment. But before taking a look at that, okay, these graphs on the right are describing the same asymptotic behavior, but to the left. That's the limit as x goes to negative infinity of f of x is equal to L, where L is finite. Okay, so the definition, the precise definition, would get updated just a little bit. Now, okay, it's to say that for any epsilon, no matter how small, for any epsilon that we choose, we can find a value n, but now notice that value n is going to be less than 0, and now we would be stating that for any x that is less than the n, the value of n that was selected, okay, for any x that is less than that n, the associated f of x on the curve is bounded between the ceiling and the floor. All right, so here's that precise definition here, as x goes to negative infinity. So now we're choosing a small positive epsilon, to create the bounds L minus epsilon and L plus epsilon, and there's a corresponding number n such that if x is less than n, then the distance between the point on the function and the horizontal asymptote becomes arbitrarily small as we would want it to get. Let's take a look at that applet in the book, that quick animation over here that it provides. It's pretty nice. So this function is undulating, but it is approaching this horizontal asymptote with the equation y equals L. Okay? And so what happens if we choose a smaller epsilon? Smaller epsilon means that the trap or the interval in the y direction is created to be smaller, and the associated value of n, the fixed value of n that we would therefore have to select as a result, like previously we were choosing delta, right? When someone gave us an epsilon, we would have to find a delta that would make the precise definition work, right? Well, with these limits here, the limits at infinity, instead of finding a delta, we would have to choose a specific value of n, or a good enough value of n, such that all values of x that are larger than that, right, make epsilon smaller. We have to update n all the way until we know that for any value of x that is beyond that n, the resulting value of y from the function is contained between this floor and this ceiling. So the geometry here is helping us to see how the definition, the precise definition, okay, actually makes sense here. Okay, so we have our symbolic precise definition backed up by our analytical geometry. And also, it's not that the limit always has to go to a finite number. It could be that the limit as x goes to infinity of f of x is equal to infinity. Now, it is also true that when this happens, that the limit goes to infinity or negative infinity, when you're taking an infinite limit, we can also state that the limit, in fact, does not exist. But I like to be a little more precise than that. In fact, in this case, you can either say that this limit goes to infinity or that it doesn't exist. I prefer to say that it goes to infinity. I prefer to reserve the statement of a limit not existing, meaning that the function is trying to go to more than one place. Okay, so we know that when we were dealing with the limits as x is going to a finite number, for instance, if we have that from the left, it's going to one finite value, but from the right, it's going to an entirely different finite value. The two values don't match each other. That's where I would say the limit does not exist, truly. Okay, even with an asymptote, if we go to a vertical asymptote, if we're going to infinity on one side of the asymptote, but to negative infinity on the other side, we would say that the limit doesn't exist. But previously we had stated that if you approach infinity from both sides of a vertical asymptote, we would state it that we would say that the limit exists and it's equal to infinity. Okay, because we have a definition for what that means. We also do have a definition for what this means in terms of our limit at infinity here. Let's take a look at a graph that would have behavior like this. Something like y equals e to the x. All right? Y equals e to the x would behave like this. As x goes to infinity, e to the x also goes to infinity. So that is to say that in terms of closeness, right, we're never going to be less than some epsilon, but instead the difference, the value, the actual output of f of x is going to be greater than whatever really large value we choose to allow it to supersede. So that is, if x is greater than, I'll modify this way. Instead of choosing an epsilon greater than 0, okay, I'm going to say, we're going to choose, let's say, m, okay, to be some number that is, very, very large. Okay, let's say we choose m is very, very large. Whatever that means, right? In quotes. Choose a large number. And for that, there is a corresponding n. So this symbol means there exists. So I'm just abbreviating that. There exists an n, then, such that if x is greater than n, okay, then f of x, the output f of x, would be greater than m. Okay, so instead of somebody choosing a small value epsilon to trap us in because we're going to infinity, instead it would be someone choosing a really large number, and we're saying, well, eventually the function will be larger than whatever number you choose, no matter how large it is. And that would be a more precise definition of a limit as x goes to infinity and f of x also goes to infinity. Okay, I won't be assessing you on the precise definitions here in this course when the limit is going to infinity. I won't be testing you on the precise definitions. I'll reserve precise definitions for epsilon delta proofs from the previous section. But I do want to introduce it here and see that there is still a common thread. Okay, we can still connect the precise definition to these types of expressions as well. Okay, so geometrically, what does this statement over here mean? If the limit as x goes to negative infinity of f of x equals infinity. Okay, well, a function that would go to the left and up, okay, would have that kind of behavior. So how about a function like this? A function that behaves like that would be y equals negative x cubed, for example. You plug in a really large but negative number here. Cubing a negative number keeps it negative, and it would still be very large. The cube of a large number is also very large. And then you take the opposite of that negative number, so you would ultimately be going towards infinity. Right? In other words, geometrically speaking, as we go to the left, the function also goes up. Okay, left and up. Limit as x goes to infinity, f of x is equal to negative infinity. So as we go to the right, the graph would go down. Okay, how about I take a quadratic that's face down like this, something like that. Okay, so how about 1 minus x squared? Okay, so right, the x squared parabola shifted up 1 unit but flipped so that it's reflected downward, for example, right? Y-intercept of 1. Okay, so we'd have that kind of behavior. And the limit as x goes to negative infinity, then f of x is going to negative infinity, so it would be a function that is down in this direction. So how about just y equals negative x squared, for example? Okay, so symbolically we can state that in all 4 of these cases here, the magnitude or the absolute value of f of x gets arbitrarily large, that is as large as we want, okay, as the magnitude of x also gets arbitrarily large, right? So as x goes to either plus or minus infinity, then f of x would go to either plus or minus infinity as well. Okay, so we've already taken a look at y equals e to the x. Okay, let's take a look at, y equals 1 over x to the r a bit. Okay, so as long as r is a positive number, like if r is a negative number, then this, something like 1 over x to the negative 2, well, that would just be the same as x squared, and we're talking about polynomial. But this is not, we're not dealing with polynomials here. So we're dealing essentially with rational functions, except this exponent here doesn't have to be a whole number. It could be a fraction, a rational number as well. So it could be something like 1 over x to the 1/2. So in other words, 1 over, okay, y equals 1 over the square root of x, for example. Okay. So what happens to those functions as x goes to infinity? Notice, of course, since the domain of this function here is that x has to be greater than 0, sorry, x has to be greater than 0, we could consider the limit of this as x goes to infinity. And as x goes to infinity, the denominator would get really, really large, okay, but the numerator stays finite, so the ratio would get very, very small and go towards 0. But notice also that because the domain is that x is greater than or equal to 0, right, we cannot plug in negative numbers into this. So we can't take the limit of this particular example as x goes to negative infinity, right? There are no negative values of x that we could even plug into this, okay? But in general, for the function y equals 1 over x to the r, where r is a rational number greater than 0, okay, the limit as x goes to infinity of 1 over x to the r, okay, is going to equal, well, it's going to equal 0, because the denominator is going to be very, very large, but the numerator is just a constant. So the numerator right now is just 1, so it's just a finite number, but the denominator is going to be very, very large, and it's going to be positive, a very large positive number. So the ratio is approaching 0. Okay, if the numerator is positive and the denominator is also going to be positive, right, then the output should be positive as well. If the numerator were a negative number, then you'd have a negative divided by a positive, and the output would be negative. It would be a very, very small negative number, but the limit would still be approaching 0. And the limit as x goes to negative infinity of 1 over x to the r, okay, as long as you're checking the domain, okay. In other words, can x be less than 0 for your particular function? Because if it can't, then this limit is going to be meaningless. We're not going to be able to evaluate it. But if x can be less than 0, similarly, as long as x can be greater than 0, we can do this, right? So we're still plugging in a very large number in magnitude, and therefore we're going to get a large number in magnitude in the denominator, right? So suppose that we had y is equal to, how about 1 over x cubed, for example, okay? If we take the limit as x goes to negative infinity of 1 over x cubed, right, the denominator is going to become very, very large, but negative, because the cube of a negative number is still negative, and the cube of a large number is still large. But the numerator is going to remain just a finite 1, just a positive number, and this ratio, dividing by larger and larger denominators, is going to result in us getting a very, very small but negative number in this case, but getting closer and closer to 0. So that's that function. Okay, the next basic function thought we'd take a look at. Okay. Oh, we can analyze this. I mean, what does this mean then for a function like this? What would that mean about its asymptotic behavior? Right? The limit as x goes to infinity of 1 over x cubed is also equal to 0. So we know that if we were to graph 1 over x cubed, we know to expect that there is going to be a horizontal asymptote, okay, a horizontal asymptote at y is equal to 0. Okay, and this function is going to approach that asymptote from both the left and the right. It turns out this particular graph also has a vertical asymptote. All right, a vertical asymptote, because x cannot be 0, it's not in the domain. So at x equals 0, there would be a vertical asymptote. Okay, and we could examine the limiting behavior as x approaches 0 from the left, as x approaches 0 from the right, in order to determine how it behaves around this vertical asymptote. But how does it behave around a horizontal asymptote? As x goes to negative infinity, that's as we go to the left, we are approaching 0, but remember we have a positive divided by a negative, so in this particular case, we're approaching 0 from below. So the graph of the function, we expect to approach the asymptote to the left, horizontal asymptote to the left, in this direction. Okay, right? It's going to be settling in towards that asymptote, but it's never going to reach it as it goes out to infinity. Remember, it's okay. The functions in general, this one won't, but functions in general can cross their horizontal asymptotes. The idea is that the horizontal asymptote is telling us where the function is heading as it goes off to the left or as it goes off to the right. Take a look how this goes off to the right. Okay, we're going to have the numerator is a positive 1, and the denominator is going to be the cube of a positive number, so it's going to be a really, really large but positive number, so we're approaching 0 from above. So this function is approaching like that. Okay, so that's describing the asymptotic behavior as x goes to infinity and negative infinity for the function y equals 1 over x cubed. Okay, now if we take x goes to 0 from the left, 1 over x cubed, of course, that's 1 over 0, but the denominator here will remain negative, so we're going to have 1 divided by a really small negative number, and that's going to output for us a really, really large but negative number. All right, so as we're approaching the vertical asymptote x equals 0 from the left, we would be going down towards negative infinity is how we would expect this to happen. This is also going to be continuous, I know, because it's not going to cross this horizontal asymptote. We can find out that if we just try to make y equal to 0, right, if we just set this equal to 0, we'll find that there's no value of x that can make that true. So this does not cross its horizontal asymptote. Okay, and for good measure, the limit as x approaches 0 from the right of 1 over x cubed. That's a 1 over 0 situation again, but here the denominator is always going to be positive, very small but positive. And so the ratio will be very large but positive as well. Okay, so here's an example of a function 1 over x to the r. We could do the same thing where r doesn't have to be a whole number, right? It could be, this could have been 1 over the cube root of x, okay? And this is still ultimately going to be true, okay? These statements right here are going to be true. X to infinity or x to negative infinity, the limit is going to be 0. Okay, now let's take a look at, so we'll be using that again and again here, some exercises in a few. Okay, well, let's take a look at the arctangent function. The limit as x goes to infinity of the arctangent of x, and the limit as x goes to negative infinity of the arctangent of x. You recall that the function y equals the arctangent of x is built by inverting the function tangent of y is equal to x, or x is the tangent of theta, where theta is an angle. So if we had, let's say, a right triangle, and the angle were called y, okay, then we're saying the tangent of that y is equal to x. Remember, tangent is opposite over adjacent. So geometrically, with a right triangle, this describes this statement here. The tangent of y is equal to x over 1. Therefore, the arctangent of the ratio x over 1, the arctangent of this ratio of opposite over adjacent, would give us a possible angle that we could have had. Okay, in this case for a right triangle, but more generally, it gives us a reference. Okay, it gives us an idea of a reference angle or a reference number that we can then associate with other angles and other numbers, okay, which might be coterminal or located in other quadrants, which geometrically would still output, okay, it ultimately still output that the tangent of those angles is equal to x. Like you might recall, like for instance, if we had the 45-degree angle here, the tangent of 45 is equal to 1. So the arctangent of 1 would be 45 degrees or pi over 4 radians. Okay, but that's not the only angle where the tangent is equal to 1. There are other angles, okay, where the tangent is equal to 1. For instance, 225 degrees, okay, which is equal to 5 pi over 4. The tangent of 5 pi over 4 is also equal to 1. But the arctangent of 1 won't be 5 pi over 4. It'll only be pi over 4. Okay? The arctangent function is built by inverting the tangent wave. Okay? The function y equals the tangent of x, or x equals the tangent of y, if you will. Okay, looks like this. Right, and it repeats. Right? It's bounded between negative pi over 2 and pi over 2 on the principal branch. Okay, and it repeats and repeats. But in order to invert it, it has to pass the horizontal line test. So we have to eliminate all the other branches and focus just on this principal branch. So we're going to invert the principal branch in order to build the arctangent function, or the graph of the arctangent function. So we switch x's and y's with each other, input and output with each other. Okay, and we get a function that sort of shaped like that, but then it has, instead of vertical asymptotes, the arctangent function has horizontal asymptotes then. Okay. Right, so if this right here is the function f of x is equal to the tangent of x, then this right here, okay, would be the function f inverse of x. Okay, that's the arctangent of x instead. So it has a horizontal asymptote y equals pi over 2. Okay, and another horizontal asymptote y is equal to negative pi over 2. We can see using this asymptotic behavior from the geometry of this curve, the limit as x goes to infinity of the arctangent of x, as we go to the right, we are getting closer and closer to the output pi over 2. And as x goes to negative infinity for the arctangent of x, we are getting closer and closer to the output negative pi over 2. So it is a function that has not one but two horizontal asymptotes associated with it. Okay, so y equals e to the x, okay, exponential growth function. There we go. All right, so it crosses at 0, 1. It goes up towards infinity to the right, but it approaches a horizontal asymptote. Okay, y equals 0 is the horizontal asymptote, but only in one direction. So we can say, let's see, the limit as x goes to negative infinity of e to the x, that is equal to 0. Okay. Similarly, it would also be true to say the limit as x goes to infinity of e to the negative x. All right, e to the negative x is the decay function instead. All right, so its graph would instead be shaped like this. That would be e to the negative x. Okay, and it is also approaching the horizontal asymptote at y is equal to 0. Okay. And back to y equals e to the x. The limit as x goes to infinity of e to the x, well, that's also equal to infinity. Okay, so this is important. Okay. And another way, again, of stating x goes to negative infinity, e to the x is 0, is that x can just go to infinity of e to the negative x, and that equals 0. All right. And similarly as well, x goes to negative infinity of e to the negative x. That's to the left. The function e to the negative x goes up towards infinity. So this is equal to infinity. Okay, so the geometry helps us to keep that clear. Okay, but this is helpful to remember as well, so we can use that. Now, what about the sine and cosine functions? Okay, so y equals the sine of x. Okay, that function starts at equilibrium. The graph of it, it's a wave, goes up, down, right? To crest, trough, and it keeps going up and down, right? And it's bounded, all right, it's bounded above by 1 at a maximum. It keeps reaching that maximum again and again, and below at a minimum of -1. Okay. What about y equals the cosine of x function by comparison? It's really the exact same wave. The same wave, except instead of starting it at the equilibrium value, we start cosine at the maximum, at the crest. So starting at 1 and then going downward, we just have the wave extend outward like this. It's the exact same wave. All right, it's the exact same wave as the sine wave, except it's been shifted by pi over 2 radians, right? The sine wave shifted to the left by pi over 2. Okay? Or the cosine wave shifted to the right by pi over 2 would give us the sine wave. And then we can modulate these, right, by choosing amplitude modulations. You know, we can multiply by positive and negative numbers in front in order to stretch these waves vertically or to flip them upside down, for instance, right? Just as we could stretch by virtue of a frequency modulation, we could stretch the input as well in order to make in order to increase or decrease the frequencies of these waves. Okay, but what happens as we go out towards infinity? Okay, so in terms of like setting a trap, like an epsilon trap, whatever we think, if we think that we know what the limit is going to be as a finite number, like let's suppose that we believe it's going to be 0, that it's going to approach a horizontal asymptote at 0. Well then, if we choose a value of epsilon that's very, very small, what we're going to expect to see, if that were true, is that eventually we would find some value of n so that any x beyond that n is always going to put us at a point that's bounded between this ceiling and this floor. But notice, because these waves keep bouncing up and down forever, they keep returning to 1, back to -1, and all the values in between, right? Then no matter what, then there's lots of small values of epsilon that could be chosen that we would never be able to be contained within. Okay, so as a result, just by using the geometry of the curve from graphing these, we can see that the limit as x goes to infinity of the sine of x, for instance, does not exist. And also similarly, the limit as x goes to negative infinity of the sine of x, that also does not exist. And the same would be true for the cosine. It's the same wave after all. Okay. So again, the reason why, geometrically, the reason why is that this is approaching more than one y value on the curve, for any value of x that we choose, right? Or for any value of n we choose, once we go beyond that n, we're going to be bouncing around continuously. We're not getting closer and closer to some particular y value, and we're also not unbounded like the exponential function was. It's not that it's always getting larger. It's that it just won't settle down. It just keeps bouncing back and forth. Okay. Alright, so we've seen some basic functions, and we'll play around with those and some examples. Let's do some examples with some fractional functions, okay, and then we'll do some other examples after that. Okay, so let's try some fractional examples. Okay, so we're taking some ratios of functions here, and the technique we're going to use here, the technique that we'll use if we have something of the form infinity over infinity that is indeterminate, okay, will be to divide all terms, numerator terms, denominator terms, divide all the terms, okay, by whatever be the highest power term, okay, that is the term that is, let's say, getting largest first, the highest power term that you can find in the denominator. There you go, all caps there. Divide all the terms by whatever the highest power term is in the denominator. Okay, let's try an example. Take the limit as x approaches infinity of 4x cubed plus 6x squared minus 2 divided by 2x cubed minus 4x plus 5. So geometrically, what we're asking here is to find the horizontal asymptote, something you would have been asked to do in a pre-calculus class. Find the horizontal asymptote of the rational function r of x is equal to this expression right here, 4x cubed plus 6x squared minus 2 over 2x cubed minus 4x plus 5. And we may recall from your pre-calculus or possibly an algebra course doing this, you can compare the degree of the numerator to the denominator when you're dealing with a rational function like this. If they have the same degree, okay, if we have the same degree, so let's say the degree of the numerator is equal to 3 and the degree of the denominator is equal to 3, okay, so what we do is we take the ratio of the coefficients. So we have the coefficient of the power term, that is the most powerful term of the numerator, has coefficient 4, and the most powerful term of the denominator has a coefficient of 2. So we get 4 over 2 is equal to 2. Then we would know to graph this, we would have a horizontal asymptote at y equals 2. This is the pre-calc way to do it. Okay, this is the pre-calc way to do it. Okay, now let's apply some calculus here. The calculus approach is to divide all the terms, numerator and denominator terms, by the highest power term in the denominator. That would be, well, 2x cubed. In fact, it's enough to just divide by x cubed. Okay, we could divide by 2x cubed as well, by the way. But this is the step I'm going to take. Divide all terms by x cubed, because that's the highest power term in the denominator. Okay, so we have the limit as x goes to infinity, and so this is the same as saying we are going to multiply the entire numerator by 1 over x cubed and the entire denominator also by 1 over x cubed. Okay, so as long as x is not equal to 0, we're allowed to do that, but x is not 0, right? X is getting very, very large here. Good point to make. This is not a technique we apply unless x is going to infinity or negative infinity. So a note of warning. This is not something we would do if x was going to 0. All right? We already dealt with if x is going to 0, you plug it in, and if you get an indeterminate form, we deal with trying to remove that discontinuity. That was another lecture from a previous day. This technique is specifically if the magnitude of x is getting large. It's only going to work in that case. Okay? So this is only if the magnitude of x is very, very large. Otherwise, this technique does not apply. The answer to why that is, well, we just took a look at what's going to happen to ratios like this if x does get really large, either positive or negative. That's going to go to 0, and that's going to be very useful. But that result is only when x is getting very large in magnitude. All right, so here's what we do. Limit as x goes to infinity of 4x cubed over x cubed. Okay, I'm going to write that out fully. 4x cubed over x cubed plus 6x squared over x cubed minus 2 over x cubed. And the denominator, we're going to have 2x cubed over x cubed minus 4x over x cubed plus 5 over x cubed. All right. Now, you don't have to write every single one of these terms like this, but I do expect to see the following. The limit as x goes to infinity. I expect to see the simplification of each one of these terms in the very next step, as well as making sure you are writing this. You must be writing the limit notation in front of each step until we actually evaluate the limit. So here's what you can write. 4x cubed over x cubed, well, that would just be 4. 6x squared over x cubed would reduce to 6 over x. Okay? And then 2 over x cubed remains 2 over x cubed. 2x cubed over x cubed is just 2, minus 4x over x cubed is 4 over x squared, and plus 5 over x cubed. So this is what I would expect to see in your work. Okay, given the original exercise, okay, and then you're dividing by x cubed on top and bottom, or multiplying by 1 over x cubed top and bottom, and then you're writing all of these terms out, and you're writing the limit notation in front as well. Okay, then the next step is to run the limit. How do we run the limit? Well, we have a bunch of little terms in here. Notice that terms like 6 over x, that would be like 6 times 1 over x. Right? If we take the limit of that, the limit as x goes to infinity of 6 times 1 over x, it's the same as 6 times the limit as x goes to infinity of 1 over x. And 1 over x is one of those cases where we have 1 over x to the r, where r is greater than 0. It's the case where r happens to equal 1. So what's this limit going to be? This limit is going to be specifically 0. 6 times 0, which is equal to 0. Right? So anytime we end up with a finite number, okay, we have a finite number in any one of these terms divided by x to the power of r, where r is a rational number greater than 0. We have r is equal to 1, to 3, to 2, and here's 3 again. And in all those cases, we have finite numbers in the numerator. So we say that each one of these terms, as x gets very, very large, each one of these terms goes to 0. And you can write it this way in your work as well. So I'm putting an arrow through there saying it's going towards 0. All right, this one's going towards 0. This one's going towards 0. Okay. So what we're really doing is, by using limit laws, we're actually applying the limit to the numerator, then the denominator, and then we're distributing the limit to each one of these. Okay, you don't have to show that you're distributing it to each one of those. I'm implying it by the notation I'm using here. So we're taking the limit as x goes to infinity of this term, and 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 this term. And several of those terms each go to 0. And what we're left with then is the limit as x goes to infinity of 4 plus 0 minus 0. All right, I'll write that part out right here. 4 plus 0 minus 0 on top, and 2 minus 0 plus 0 on the bottom. Okay, and that, of course, just simplifies to 4 over 2. Notice where I stopped writing the limit notation. Once we ran these limits, and the limit of a constant is the constant, was another limit law. The limit of 4 as x goes to infinity is just 4. So now that I've actually run the limit, that's when I stop writing limit. So the limit has been run, and now we're just evaluating this, and it comes out to 4 over 2. Well, 4 over 2 is equal to 2. In other words, the horizontal asymptote, as x approaches infinity, as this rational function goes off to the right, it's approaching the horizontal asymptote with equation y equals 2. The same as we found in our pre-calculus course when you study the rational functions there. Okay, so now to get away from what we did in pre-calculus and say we can apply these same techniques to a wider variety of functions as well. Let's try another example. Okay, I'm going to take an example from your worksheet, in fact, for this one. This example right here. Okay, so notice that the exponent is 3/2 in the denominator, plus we have this extra square root floating around in the numerator. So this is not a rational function, okay, because we're dealing with more than just polynomial. We have more than whole number exponents, okay. But the technique we applied can still be applied to this example as well. Okay, so let's try this one out. Limit as t approaches infinity of t minus t root t over t to the 3/2. Oh, sorry, that was 2t to the 3/2 plus 3t minus 5. All right, 2t to the 3/2 plus 3t minus 5. Okay. First, I'm going to do a little bit of algebraic simplification here in the numerator. Okay, we have t to the first times t to the 1/2 because the square root of t is the same as t to the 1/2. So we can add those exponents. So in the numerator, we have t minus t to the 3/2, and in the denominator, we have 2t to the 3/2 plus 3t minus 5. So now we have we have terms on top where the exponents go up to 3/2, but terms in the denominator, the exponents go up to 3/2. So the highest power term of the denominator is 2t to the 3/2. Right? That's the highest power term we have in the denominator. The highest power term in the denominator. Okay, so I'm going to divide all terms. Okay, I don't need to divide by the 2 as well. You can, and it would still work, but it's sufficient to divide all terms by t to the 3/2. Okay, so I'm going to want to show that. The limit as t goes to infinity. Okay, so here's an acceptable way to show that. Okay, I'm going to multiply the top by 1 over t to the 3/2, and I'm going to multiply the bottom by 1 over t to the 3/2 as well. And we'll do the distribution and clean that up. What is t divided by t to the 3/2? Well, that would be 1 over t to the 1/2, or 1 over the square root of t, minus t to the 3/2 over t to the 3/2, so that's just 1. Down here we have what, 2t to the 3/2 over t to the 3/2 is 2, and then plus 3t over t to the 3/2 is 3 over t to the 1/2, or 3 over the square root of t, minus 5 over t to the 3/2. Okay. All right, so now similarly to what we were looking at before, we now have a bunch of terms here where we have finite numbers in the numerator and the variable in the denominator, where the variable is to some rational exponent. All right, so we have rational exponents here. So for instance, we have the exponent 1/2, right, 1/2 and 3/2. Right, so we're dealing with things like y equals 1 over t to the r, where r is greater than 0. And as t goes to infinity, okay, as t goes to infinity of this expression, each of these terms are therefore going to go to 0. Okay, so let's now run the limit. Running the limit on this term, this is going to go to 0. On this term, this is going to go to 0. And on this term, this is going to go to 0. And of course, the limit of a constant is just the constant itself. So the 1 is going to be a 1 and the 2 is going to be a 2. So we have 0 minus 1 over 2 plus 0 minus 0. I don't have to write limit anymore. You don't have to either, because we have now run the limit. Okay? And this just equals what? Negative 1/2. Okay? All right, let's try another example, a different type. What about if we take limit as x goes to negative infinity? Okay, let's take the limit as x goes to negative infinity. Well, let's do a different function here. How about 1 plus x to the 6th over x to the 4th plus 1? Okay, so the magnitude of x is getting arbitrarily large. Okay, so we can apply that same technique. We can divide. Okay, we can divide by the largest power term, okay, in numerator and denominator, which in this case then, okay, in this case is x to the 4th. So we have the limit as x goes to negative infinity of 1 plus x to the 6th over x to the 4th plus 1. Okay, so on top we have 1 over x to the 4th. On the bottom, 1 over x to the 4th as well. Okay, and distribute that term. So we have the limit as x approaches negative infinity of 1 over x to the 4th plus x squared over 1 plus 1 over x to the 4th. Now we can run the limit. Okay, we have a bunch of, again, situations. We have a couple terms here, 1 over x to the r, where r is greater than 0. This will go to 0 whether x goes to positive or negative infinity. Right? So this term goes to 0, and this term goes to 0, but that leaves us with an x squared. So we still have to evaluate further. The limit as x goes to negative infinity of x squared over 1, or just of x squared. What is that going to? Well, as x gets large, x squared gets very, very large, and the square of a negative real number, that's going to be a positive number. So this is going to positive infinity. Okay, so that would be the answer there. Another thing I want to look at in this particular exercise, I don't want to say what if, I want to say why not. Okay? Why didn't we divide instead by the highest power of the numerator? Why not divide by x to the 6th instead when we were doing that? The limit as x goes to negative infinity of x to the 6th, all right? The other way around, right? 1 plus x to the 6th over x to the 4th plus 1. What would have happened if we divided by the highest power term in the whole fraction instead? Right? What would happen? We're going to get the limit as x goes to negative infinity. Okay, and now we're going to have what? 1 over x to the 6th plus 1 on top. But on the bottom, notice what we're going to have is 1 over x squared plus 1 over x to the 6th. And now, if we run each of these limits, we get 0, 0, and 0. And what's the problem with this? This is equal to 1 over 0, and that's undefined. And undefined does not mean it goes to infinity necessarily. Okay, so in other words, we don't have a result from this. Okay, this is inconclusive. And for that reason, that's why we do not divide by the highest power term we can find anywhere. We only divide by the highest power term in the denominator. Notice that by dividing by the highest power term in the denominator only, it guarantees that the denominator will not be 0. Right? Instead, we'll be left with whatever the coefficient of that highest power term is. So our denominator will remain finite. Okay, so that's that example. All right, let's take a look at some more examples, of course. Okay, there's still plenty more interesting examples for us to look at. Yeah, so the next one, take a look at, is limit as x goes to infinity, the square root of 9x to the 6th minus x over, let's see, x cubed plus 1. So for this one, consider x is getting very large and positive, right? X is going to be positive. And the largest power term in the denominator is x cubed. So we're going to want to divide all terms by x cubed. All right, so we'll set it up like we did in the previous exercises. So we have 1 over x cubed on top, and we have 1 over x cubed on the bottom as well. Okay, so now notice that what's going to happen in the numerator, though. Okay, in the numerator, we're going to have a square root of 9x to the 6th minus x, and that's going to be over x cubed. But how do we get the x cubed inside of the square root? Because then we can take the ratio of each of these terms over the x cubed. Well, note that x cubed is equal to the square root of x to the 6th. Okay, as long as x is greater than 0, this is going to be true. Okay, why not when x is less than 0? Well, let's take a look at that in the next exercise. Okay, so x cubed itself is the same as the square root of x to the 6th. So dividing by x cubed up here is the same as dividing by the square root of x to the 6th. So now we have this. Right? So we replaced x cubed by the square root of x to the 6th, and that's going to allow us to combine these under the square root. Meanwhile, in the denominator, we would have 1 plus 1 over x cubed, and I'm not going to run that limit yet. I want to deal with the numerator further. So the numerator is now the square root of 9x to the 6th over x to the 6th minus x over x to the 6th, and all of that is contained within that square root. Okay, and that'll clean up a bit. The limit as x goes to infinity. Then we have the square root. In the square root, we're going to have 9 minus 1 over x to the 5th, and the denominator is just 1 plus 1 over x cubed. Now let's run the limit on each of these terms. Remember that by continuity, we can pass the limit into the square root brackets, and then we can take the limit of each of these terms as well, because the square root function is continuous close to 9, which is where this input is going to go. So by continuity, we are allowed to push the limit inside the square root and do these term by term as well. Okay, so what does that give us? Well, this term here, 1 over x to the 5th, that will go to 0, and 1 over x cubed will also go to 0. Okay, so we've now run the limit. We don't have to write limit anymore. We have the square root of 9 on top and just 1 on the bottom, and that's going to equal 3. So the value of the limit here is 3. All right, now let's consider that negative situation. All right, let's consider the limit as x goes to negative infinity. Okay, of the same expression, in fact, we can do 9x, square root of 9x to the 6th minus x over x cubed plus 1. Okay, we're still going to start out the same way. Okay, I'll leave that for your notes. Okay, well, all right, the original just like that for your notes. Okay, but now the first step is the same first step we've been using. Right, dividing all terms, that is essentially dividing the numerator and denominator by the highest power term from the denominator, which is 1 over x cubed in this case. Okay, but here's where things differ. X is negative, right? Notice, x is less than 0, right? What happens if, let's start with a square root. What happens if you take the square root of x squared if x is less than 0, right? For instance, let's take x is equal to negative 1. If x equals negative 1, what is the square root of x squared? It would be the square root of negative 1 squared. And what's the square root of negative 1 squared? Is the square root of x squared always just going to equal x? Well, if x is equal to negative 1, that would be saying that the square root of negative 1 squared is equal to negative 1. But is that true? You can check your calculator if you're not sure. The square root of negative 1 squared is not equal to negative 1. It's equal to 1. Right? Because the negative 1 squared, by order of operations, is 1, and the square root of 1, the square root is a function. It can only output one possible value for any input. The square root of 1 is 1. So the square root of x squared does not equal x if x were negative. The square root of x squared is equal to the absolute value of x in case x was negative. But if we already know, okay, if we already know that x was negative to begin with, if we already know x was going to be negative, right, then instead of putting the absolute value bars around this, we can instead say, well, whatever x was, since it was negative, we know it can't output a negative, so we're going to take the opposite of whatever x is. Okay? So, in other words, if we already knew that x was going to be negative coming in, we could have said, well, whatever x is equal to, let's just take the opposite of that, and that would be equal to our answer then. And that would make it work. Since x is negative, we know it's negative, right? X is going to negative infinity, and therefore by closeness to negative infinity, okay, quote unquote closeness to negative infinity, x is already negative. And we need to take x cubed and push it into a square root, okay? The square root of x to the sixth, is that equal to x cubed? Not quite, okay? For instance, what's the square root of negative 1 to the sixth equal to? Okay, is that equal to negative 1 to the third? Well, negative 1 to the sixth is 1, so this is the square root of 1, and the square root of 1 is equal to 1. But negative 1 cubed, well, that's equal to negative 1. So how do we make this work? We take the opposite of what x is, okay, and cube it, or the opposite of x cubed. So whatever x was, we take the opposite of that, and now it's correct. The square root of x to the sixth is equal to negative x cubed if x was already negative, and x is negative. So now we can run this limit. The limit as x goes to negative infinity, okay, we have on the top, let's take it this way, square root of 9x to the sixth minus x over x cubed, but x cubed, because x is negative, x cubed is the same as negative the square root of x to the sixth. All right, I'm just applying the negative now to the other side. Okay, because I needed to push it inside the square root, and because x is negative. If that negative sign wasn't there, then the output of this would not be a negative number. It would be a positive number. But we need x cubed to be negative because the cube of a negative is negative. So we needed to put that sign there. All right, now the denominator, no such concern, no such issue to deal with in the denominator because we didn't have any square roots going on. Right, and by the way, this is only really an issue when you have that that this is to an odd power, right? Because if this were x to the fourth, right? If this were x to the fourth, it wouldn't matter because the fourth power of a negative number is positive. So if you had something like x to the fourth, you could just say that that's the square root of x to the eighth, and that would be true whether x was positive or negative. Okay, because x to the fourth is always going to be positive anyway, since x is a real number. Okay, but it's something to watch out for, and it's why I'm including this example here as well. Okay, something for you to think about. So the limit as x goes to negative infinity now. Let's push this inside of that square root. I'm going to put the negative in front of the square root. Then inside the square root we have 9x to the sixth over x to the sixth. Okay, right. So we're now dividing minus x by x to the sixth as well, right? Minus x over x to the sixth. The denominator would be 1 plus 1 over x cubed. Okay, let's clean that up a little bit, and then we'll run the limit. X goes to negative infinity. We have a negative in front. Square root of 9 minus 1 over x to the fifth over 1 plus 1 over x to the third. Okay, run this limit from here, and what do you get? Okay, try running this limit right now. Okay, and let me know what you get. Okay, so we can distribute the limit into the square root and term by term by the limit laws. So we can take the limit of each of these two terms. They will each go to 0. Right? They are both 1 over x to the r. R is a rational number, and x is going to be arbitrarily large in magnitude, in this case going to negative infinity. So each of these goes to 0. So we're left with negative the square root of 9 minus 0 over 1 plus 0, and evaluate that, we would get negative 3. So this limit's equal to -3. We would not have gotten that negative, or we might have missed that negative if we didn't do this analysis of -x cubed being the square root of x to the 6th, right? That negative showed up because of that. Okay, so it's something to watch out for. Okay, something to watch out for when you're plugging in negative numbers and you're dealing with even roots, in this case a square root, because the output of an even root will always be non-negative. All right, let's take a look at some more examples and some more examples of other complications. Let's take a look at infinity minus infinity. Infinity minus infinity is indeterminate, an indeterminate form. This would be our third indeterminate form. We've already seen 0 over 0 previously, of course, and we've seen infinity over infinity. That's like what we're dealing with in this section, right? If you run the limit as x goes to infinity, the numerator and the denominator, for instance, okay, you might get infinity divided by infinity. This one right here. This would go to infinity over infinity. Okay, and it actually equaled a finite number, and we had to find that finite number. It turned out it was equal to 2 in this example. Okay, infinity over infinity is indeterminate. It could equal infinity, it could equal negative infinity, it could be 0, it could be some other finite number. Okay, so it is indeterminate. Well, infinity minus infinity is also indeterminate. Okay, and here's an example where we would get infinity minus infinity. Limit as x goes to infinity of the square root of 4x squared plus 3x, and then outside the square root we have minus 2x. So if we were to run the limit right now, we would find infinity minus infinity, but that's indeterminate. Okay, so is this equal to 0? Is it equal to something else? How do we find out? Well, we have, here's a hint here, we do have a square root there, and we have 2 terms. Okay, if we rewrite this as a ratio, okay, by putting it over 1, now we can deal with this ratio by multiplying the top and the bottom by what quantity? What do we call this? What's the term that we have? The word for the top and the bottom. What are we going to multiply this by? The numerator. Okay, in order for us to FOIL this, which is going to allow us to eliminate this square root, we're going to multiply by the what? And we're going to multiply by the conjugate of the numerator. That is the square root of 4x squared plus 3x, and then plus 2x. Okay, is the conjugate of the numerator. All right, the conjugate. Now we multiply both the numerator and the denominator by that. So this is transforming this 2-term infinity minus infinity situation we have here into a ratio, a fractional expression. And by transforming it into a fractional expression, we can apply the techniques that we've already been using to this point. Oh, and by the way, if I go back one moment here to this step, what if this was a plus right here? Then what would happen? Now, notice the limit of this is just infinity, because we would have infinity plus infinity, square root of that is infinity. And then adding to that another infinity. And infinity plus infinity, that's not indeterminate. Infinity plus infinity, well, that would just be infinity. All right? So it's not just that we have 2 terms here, right? If this was going to, negative infinity, that could have changed it up, but it's not in this case, okay? So we had infinity minus infinity. Now we're going to use the conjugate, top and bottom, in order to create a fractional expression. So the numerator, by FOILing this out, the numerator will be 4x squared plus 3x, and then the outer and inner terms cancel each other out, and we're left with a minus 4x squared. And the denominator, we have the square root of 4x squared. Sorry, that should be a 4x squared plus 3x plus 2x. Okay, so the 4x squareds, they cancel each other out now. Okay, and if we were to try to rerun the limit, we're going to get now infinity over infinity, an indeterminate form. But how do we run this limit now? we can divide by the highest power term in the denominator. Now, the highest power term in the denominator, okay, would either be this 2x right here, it's x to the first, or not x squared, but the square root of x squared. The square root of x squared, which, since x is positive, the square root of x squared is equal to x. Right? Of course, if x was negative, then the square root of x squared would have equaled negative x, or the opposite of x. Okay, so we can divide everything by x, essentially, which is the square root of x squared, if we need it. Okay, so the numerator is 3x. The denominator, right, we have, all right, I'll go ahead and I'll put that in this, right up here. So I'm going to multiply by 1 over x on top and 1 over x on the bottom as well. I've canceled out those terms already. Okay, so we have 3x over x. Okay, I'll write that out. 3x over x. And then down here, we have the square root of 4x squared plus 3x. That is divided by, it is divided by x, but to get it to combine into the square root, it is the square root of x squared that we're dividing by. And then we have plus 2x over x. So that's the limit as x goes to infinity. The numerator is 3. The denominator we have inside a large square root bracket. We have 4x squared over x squared plus 3x over x squared. And then plus 2. Okay. So that is the limit as x goes to infinity of 3 over the square root. Okay, the square root of 4 plus 3 over x, and then outside the square root we have a plus 2. So now we run the limit on this term right here. This goes to 0, and the limit of the other terms, well, those are all constant. Okay, so this limit is equal to 3 over the square root of 4 plus 2. So 3 over 2 plus 2, which is equal to 3/4. So we had an indeterminate form of infinity minus infinity, and we applied the conjugate here. That was the technique that we used. Then we divided by the highest power term in the denominator, which in this case required us converting x into the square root of x squared. Because x was positive, that was true. We ended up with a finite limit, and that was equal to 3/4. Next example, let's let x be negative, but not for that expression, okay? For a different expression. X goes to negative infinity of x plus the square root of x squared plus 2x. Now, as x goes to negative infinity, we'll note that the first term, do this in green, the first term will go to negative infinity, and the second term, this radical here, which always outputs a positive, notice that we've got x squared plus 2x. That itself is going to what? Infinity squared minus infinity, right? Well, this is going ultimately to infinity because the square of a large number is always larger in magnitude than the number itself. So this is ultimately going to infinity, and the square root of infinity is infinity as well. Okay? So we have negative infinity plus infinity. Well, that's indeterminate, right? That would be an indeterminate form. Negative infinity plus infinity, which is the same as infinity minus infinity, right? It is indeterminate. And we have a similar situation to what we had a moment ago, where we have square root here, 2 terms. So let's apply the same technique. We'll multiply by the conjugate again. Put this over 1. And in this case, the conjugate is x minus the square root of x squared plus 2x. And the denominator is x minus the square root of x squared plus 2x. So we have the limit as x goes to negative infinity. The numerator will be x squared minus the quantity x squared plus 2x over x minus the square root of x squared plus 2x. So the x squareds cancel each other out, and we distribute that minus sign. We have negative 2x over x minus the square root of x squared plus 2x. Now, run the limit again, right? We get positive infinity on top, right? And on the bottom, though, we're going to get a negative infinity minus infinity, right? So if we run the limit again, we're going to get infinity on top, but on the bottom, we're going to get negative infinity minus infinity, which is negative infinity. Okay? The fact that this has a negative in it doesn't change the fact that this is still indeterminate. It's indeterminate. But it's of a different form, infinity over infinity, and that's where we can divide by the highest power of x in the denominator. In this case, what's the highest power of x in the denominator? Okay. It's just x. X, which also, in terms of a square root, is the square root of x squared, right? But x is negative. And if x is less than 0, like negative 1, for instance, then the square root of x squared is not x. The square root of x squared then is the opposite of x. Okay? Or x is equal to the opposite of the square root of x squared. So we have the limit as x goes to negative infinity of negative 2x over x minus the square root of x squared plus 2x. We would multiply the top and the bottom by 1 over x, okay? And we can apply that x to each term. The limit as x goes to negative infinity. On top, we have negative 2. On the bottom, we're going to have 1 minus, right, the square root of x squared plus 2x, okay? And then the x down there, in order to combine it into the square root, we need to replace that with a square root. Since x is negative, that means we're replacing this with negative the square root of x squared. Run the limit from here. Write this down. Okay. Pause the video. What do you get if you run this limit as x goes to negative infinity? So what I'm getting is that we have the limit as x goes to negative infinity of negative 2 over, let's see, 1 plus the square root of x squared over x squared plus 2x over x squared. All right, it's the limit as x goes to negative infinity of negative 2 over 1 plus the square root of the quantity 1 plus 2 over x. 2 over x is going to go to 0 as x goes to negative infinity. Okay, and all the other constants, they're just going to remain constant. So we get negative 2 over 1 plus the square root of 1. And that's negative 2 over 2, which is equal to negative 1. Okay, so the answer I'm getting here is that we're going to get negative 1 as the output to this limit. Okay, next example. Limit x goes to infinity of the quantity, the natural log, right, of 3 plus 2x minus the natural log of x minus 1. So if we run the limit on these terms, we're going to get the natural log of a really large number. Okay, well, the natural log function, right, remember the graph of the natural log, y equals the natural log of x. Right, it has a vertical asymptote at x equals 0, but no horizontal asymptote. The limit as x goes to infinity of the natural log of x is equal to infinity. So this is going to infinity, and then we're subtracting, and this is also going to infinity. So we have an indeterminate form. Now, how do we deal with the indeterminate form here? It's not going to be the conjugate. It's going to be the law of logarithms. Okay? Using the law of logarithms that says when you have a log with, let's say, a base of b of, let's say, an argument a minus another log of the same base but of a different argument, you can combine them with a log of the same base where you take the ratio of the arguments. Okay, so we can do that. Law of logarithms. So in this case, we'll have then the limit as x goes to infinity of the natural log of the ratio 3 plus 2x over x minus 1. Now, by continuity, right, by continuity of the function y equals the natural log of x, we can pass the limit into the natural log. Okay. Okay. It's because the natural log function would be continuous as long as the argument is greater than 0. And when we run the limit on this argument, as long as we get a value that's greater than 0, then it would have been continuous, so we're allowed to pass the limit in. Okay, that was from the section on continuity prior to this section. So this is the, I'm going to pass the limit now. So we have the natural log of the limit as x goes to infinity of 3 plus 2x over x minus 1. Okay, so this argument in here is rational, in fact. Okay, it's an easy limit to do. Okay. So I'm going to divide all the terms by the highest power of x in the denominator, which is just x in this case. So this is 3 over x plus 2 over 1 minus 1 over x. Right? So I've divided all those terms there now by x. And now we can run the limit on 3 over x as x goes to infinity. That limit is 0. For 1 over x, also 0. Okay, and for the constants, they remain constant. So we end up with the natural log of 2 over 1. In other words, the natural log of 2. Okay, and so that's the output, natural log of 2, okay, which is a finite number. Okay, so now let's take a look at a couple other interesting examples. Limits at infinity. Limit as x goes to infinity of, let's say, e to the negative x plus 2 times the cosine of 3x. Okay. The limit of the first term, e to the negative x, remember, as x goes to infinity, e to the negative x, that's going to 0. All right, recall that e to the negative x is the same as 1 over e to the x. All right. So if e to the x gets really, really large, this ratio gets really, really small. And that's what's happening here. And what about the other one? We have a cosine wave, right? The wave up and down and up and down, okay? It is not approaching any limit, right? This limit here does not exist. And then we have to take the sum of the two. A finite number plus something that doesn't exist, well, ultimately the sum is therefore not going to exist. So this does not exist. Well, take another quick look at an exponential function that you had in your worksheet. Notice I put this one here for you. Okay, it is a fractional expression. Apply the same technique we've been applying on fractional expressions. Divide by the highest power term in the denominator, right? That's which of these terms in the denominator is getting large the fastest. Which is getting the largest the fastest. Okay, and that would be, look, we have a growth term. Since x is positive, going to positive infinity, then e to the 3x is growth, okay? And e to the negative 3x is decay. So e to the negative 3x, well, that one's going to 0. But e to the 3x is going off to infinity. And it's getting there very fast. So that is the highest power term. So you can go and you can divide all of these terms in this expression by e to the 3x, because that is the highest power term in the denominator. Okay? So it's not polynomial, right? It's not one of these radicals. It's an exponential function, an exponential term instead, but you can still apply the technique there. Divide all these terms by e to the 3x, and then run the limit. And so there, you'll be finding terms like 1 over e to the 6x, for instance. Okay, but we already have 1 over e to the x, right? The limit as x goes to infinity of 1 over e to the x is equal to 0, right? So that would also be true for something like the limit as x goes to infinity for 1 over e to the 6x. That would be true as well. It's going to go to 0 because the denominator is getting very, very large while the numerator is staying finite. Okay, a couple more examples of some different types here maybe to look at. This is also from the worksheet. What is the limit as x approaches 0 from above of the arctangent of the natural log of x? We've already discussed both the arctangent function and the natural log of x function. So I believe you should be able to evaluate this limit right now. But there's another thing I want to talk about here, and that's your notation. How are you going to show your work here? We have a composition of functions here, right? We have something like f of g of x, and we're taking the limit of that as x goes to infinity. Okay, and we said previously with limit laws, how do we run this limit? We're not plugging x into the arctangent function, we're plugging x into the natural log function, and then the result of that, the output of the natural log, is then being plugged in to the arctangent. Okay, so what we can do is, like, let's say we let y equal the natural log of x. Let y equal the natural log of x. Then, by continuity of the arctangent function, we can move the limit into the inner function, because the arctangent will be continuous from negative infinity to positive infinity, so it's okay. So we have the arctangent of the limit as x approaches 0 from above of the natural log of x. And what is this limit? Recalling that the natural log function, again, looks like this. Its graph. It approaches a vertical asymptote, x equals 0. Okay, so the limit as x goes to 0 from above of the natural log of x is equal to negative infinity. Okay, but we can't write this. We can't write this as the arctangent of the negative infinity. That is wrong, because you can't plug in negative infinity, right? So this is notationally incorrect. Okay, notationally incorrect, right? So we cannot plug in infinity or negative infinity. It is not a value you can plug in. You can get negative infinity from a limit, though, from a limit. And so that's the way we're going to look at this instead. You cannot write it this way. What can you do, though? Write this as, so we know that the argument is approaching negative infinity. The output of the natural log is approaching negative infinity. So we can choose a symbol for that argument, not x, because x was already used. Another symbol we can choose for the output, the result of that limit. Okay, so we can write a new limit now as our output of natural log approaches the negative infinity, because that's what's going to happen. And then we are running that limit on the arctangent of y. And this would be notationally correct. All right? Notationally correct. Right? And that makes us mathematicians happy. Yay. Okay? This is the correct way to do that, right? When you're dealing with that composition. Okay, so we name the output of the inner function a new name. We give it a variable name that wasn't already used. That would be a way to do that. Okay? Then, and then ultimately you can run the limit on the outer function then as your new variable approaches what the output is approaching of the inner function, just like I've done here. Okay, now what is this limit? Now we're taking the arctangent function, right? We have our arctangent function like we had from before. Okay, this is the arctangent of y function. Let's say I call this z equals the arctangent of y. In other words, this is the z-axis and this is now the y-axis because I've changed the input variable. All right, this is pi over 2 and this is negative pi over 2. So as the input goes to negative infinity, the output is approaching negative pi over 2. Okay, very good. All right, I have just one more to look at here. The limit as x goes to infinity of the cosine squared of x over x cubed minus 1. Okay, if we try to run this limit right now, the numerator, notice what's happened to the numerator, it does not exist. Meanwhile, the denominator is going to infinity. Does that mean the result does not exist? Well, it did mean that if we were adding them together. If we were adding these together, that meant doesn't exist. But this does not necessarily mean that this ratio does not exist. Because cosine squared, because cosine squared is bounded. Cosine squared is never going to be greater than 1, and because it's the square of a real number, it'll never be less than 0. So we can use boundedness of the numerator here. Since we couldn't do anything else otherwise, we can check with the boundedness if that's going to help. So if cosine squared of x is bounded between 0 and 1, then if we divide by x cubed minus 1 on all sides, then we now have bounds for our function. Okay, and then our limit, the limit as x goes to infinity of the cosine squared of x over x cubed minus 1, we can bound between the limit as x goes to infinity of the ceiling function 1 over x cubed minus 1 and the floor function limit as x goes to infinity of 0. Right? Because 0 over x cubed minus 1 is just 0. Right? What theorem is this that we're applying? What is the name for this theorem that we're introduced to in a previous section, where we are bounding our function between a ceiling and a floor and then running the limits? And we're going to check to see what is the limit of the ceiling, what is the limit of the floor, and as a result, what is the limit of our function? What name do we have for this theorem? In this course, we call this the squeeze theorem. Sometimes it can be called the sandwich theorem. We called it the squeeze theorem. Okay. You take the limit of the floor, the limit of a constant is just going to be the constant. And how about on the right? You can divide by x cubed, right? So we get the limit as x goes to infinity of 1 over x cubed over 1 minus 1 over x cubed. This goes to 0 here, this goes to 0. So we end up with the ratio 0 over 1, but 0 over 1 is just equal to 0. So our limit is bounded between 0 and 0, so it is being squeezed, and therefore our limit must also be 0. Okay? So it was not that it didn't exist as a ratio. Okay? In this case, it ended up going to 0, and we showed that it went to 0 by the squeeze theorem. Okay? Every so often, the squeeze theorem is going to show up when you have a function that's not behaving so well, but it is bounded, which a lot of times would be when there's a trigonometric. The sine function or the cosine function are the classic examples that lead us to a squeeze theorem. Okay, and similarly, cosine squared. If this was just cosine x, the bounds would have been -1, +1 for cosine x. But because it's cosine squared, the bounds are 0 and 1 instead. Okay, so that is plenty for this section, right? You have a lot of tools that you can use, some new techniques you can apply, and a whole variety of functions you can now evaluate when the limit is going, when the limit of the variable x, let's say the input variable, is going to infinity or to -infinity. Okay, check out the homework and the worksheet as well that I provided for you. Let me know if you have any questions, and take care.